In this video, we discuss graph representations and their C++ implementations.
A graph is a finite set of points, referred to as vertices or nodes, in space interconnected by a set of lines, referred to as edges. So, a graph G consists of a set V, the vertex set, and a set E, the edge set. In practice, we often draw a vertex as a circle instead of a point and label it inside the circle. This is a directed graph. We use an arrow instead of a line to represent an edge. In this graph, the vertex set has vertices 1, 2, 3, and 4. The edge set has edges 1, 2, 1, 4, 2, 2, 3, 1, 4, 3, and 4, 2. The red arrows show a path from 1 to 3, and the path 1, 4, 3. 1 is a cycle as we can start from vertex 1, traversing through vertices 4 and 3 and going back to 1. 2 is adjacent to 4 as there's an edge from 4 to 2, but 4 is not adjacent to 2 because there's no edge from 2 to 4. This is an undirected graph. We use lines to represent edges. The vertex set has vertices 1, 2, 3, 4. 1, 2 is an edge, so is 2, 1, 1, 4, 4, 1, 2, 4, and 4, 2 are all edges. There is no edge from 3 to any other vertices. It is an isolated vertex. A graph can be represented by an adjacency matrix. This is an undirected graph with vertices A, B, C, D, and E. The corresponding adjacency matrix is shown here. We use a 1 to denote an edge connecting two vertices and a 0 to represent the entry of no edge connection between two vertices. So, the entry for AA is 0, AB is 1, AC is 1, and so on. The matrix is symmetric. As you can see, BA and CA are also 1. AE is 0, so EA is also 0. Alternatively, one can use 1 to represent a connection, and infinity to represent no connection. In this representation, the entry AA is infinity and AE is also infinity. This is the adjacency matrix for this directed graph. The matrix is not symmetric. AB is 1 as there is an edge from A to B, but BA is 0 as there is no edge from B to A. Again, alternatively, we can use infinity to represent no connection. This is the adjacency matrix for this directed weighted graph. The entry in AB is 4, which is the weight of the edge from A to B. The entry in AC is 3, and so on. The entry is 0 if there is no edge between the two vertices. For example, CA is 0. In practice, the weight at an edge could be the length from one vertex to another. Using infinity to represent the absence of an edge between two vertices is a better representation as it resembles reality more. For a directed graph, to find out the vertices, or nodes, connected to a node, we need to scan the row and column of the vertice. If there are n vertices, the time complexity of the operation is theta 2n, which is equal to theta n. The space complexity is the n square as there are n times n entries in an adjacency matrix. A graph can also be represented by linked lists. We use adjacency lists to represent a graph as an array of linked lists. For this undirected graph, this is the adjacency list for vertex A, which has neighbors B, C, and D. This is the list for vertex B, which has neighbors A and E, and so on. For this directed graph, this is the adjacency list for A, which has neighbors B, C. B has a neighbor E. C has neighbor D. D has neighbors B and D. E has no neighbor. For a weighted graph, we include the weight of the edge in each node. For example, the weight of the edge AB is 2 and AC is 4. The weight for BE is 3 and so on. In this representation, there are n lists where n is the number of vertices, so the time complexity of finding a node is theta n and the space complexity is theta n times m, where m is the number of edges. Next, we discuss C++ implementations of the graph representations. The implementation of an adjacency matrix is straightforward. We simply use a two-dimensional array to represent the matrix. We have discussed this in the video of greedy algorithms and Dijkstra's shortest path algorithm. Implementations of adjacency lists are also quite simple. We will use this graph as an example to explain the implementation.
This graph has 5 vertices labeled as 0, 1, 2, 3, 4. And these are the ways of the edges. So 0 to 4 is 10, 0 to 1 is 50, 0 to 2 is 30, okay, and so on. Now, the code here shows the implementation of the adjacency list. Okay, so we have to include these headers. Okay. Then this header is for utilizing the list, okay, because basically we need an array of lists. So first we declare a class node. So this node, okay, has the label vertex, okay, and its label like 0, okay, it has a label 1, okay, and also it has weight, okay, so this is the weight of the edge, okay. So node means this 0 to 1 and the weight 50, okay, that we called the class node. So it is not exactly a vertex, okay. So it includes its label and the weight, okay. And this is the constructor. So we supply the vertex label V, the label W, and the weight N, okay, to construct this node. Now, this is the class edge. Class edge is easy to understand. The variable data member start var is the starting vertex. End var is the end vertex. Weight is the weight. Okay, like this edge. Okay, the start vertex is 0. The end vertex is 1. The weight is 50. Okay, so it is quite straightforward. So that's the class edge. Okay. And then now this is the graph, the class graph representing this graph. Okay. So it has private data members, and nodes is the number of nodes, a number of vertices in the graph. Okay, more precisely, and nodes means number of vertices. Okay. And edges is the number of edges. Okay. So this is a little bit confusing, and nodes. Maybe a better notation is to use n vertices. Okay. Because this node is not exactly the same as this node. So we have a public data member. We call it list array, okay, of data type node. Okay. So basically, we need an array of this. Okay. So this declare the array of list. Okay. And the constructor. Okay. This is the constructor. We pass in the edges of the graph, and NG, the number of nodes, number of edges, and NV, number of vertices. Okay, so basically we set n nodes to NV, n edges to NE, and then we allocate a new list. The list array will consist of the array of lists. Okay, so this is one list, another list, another list, another list, another list. Okay, so this constructor construct an array of lists, okay, to try NV lists. And then we put the edges or the nodes into the appropriate list. Okay. So to try there are that many edges, so we pass in the edges, we just put them into the list. Okay, so that's for each edge we have the starting vertex. Okay, so that is equal to that object start word. Okay, the end word, okay, is equal to that edge start the end word. Okay, and the weight is the weight of that edge. Okay, so we get these values, and then we create a new node using this start vertex, the weight, and the end vertex. Okay, and then we push this node into the corresponding corresponding list. Okay, the list start word. Okay, so each list, okay, corresponds to a vertex. Okay, so, and then we just push a node into that list. So that's the constructor. So if you want to display the list, okay, that's simple. You can have a member function display to display it. So today there are n nodes. Okay, basically this is n vertices. Okay, and the notation is a little bit confusing. Okay, and to do that, to do the display, we use an iterator IT to iterate through each list. Okay, so today there are n nodes lists. Okay, n nodes is equal to the number of vertices. Okay, so we start from begin and goes all the way to the end of the list. Okay, so we just let A to be what the iterator is pointing at. Okay, so that means we are considering, say, a node. Okay. And then we print out that node's vertex, okay, and the label and the weight, okay, with parentheses. Okay. So we do that for all that list. Okay. And here's the destructor. We just delete the list away, okay, to deallocate memory. So this is an example of showing this implementation. So we have to provide edges to the graph, to construct the graph. Okay. So here the edges x, y, w, it is from 0 to 1 with weight w. Okay, the start at the start vertex, the end vertex, the weight. Okay. So this is the edges. These are the edges. Okay, start word, end word, and weight. Okay. So this is 150 corresponding to say this 150. Okay, so next will be 2 30, the other edge. 2 30, and the next is 3 100, 4 10, 3 100, okay, 4 10. Okay, and for 1 there's no outgoing edges from 1. Okay, and for 2 we just have 1. There's 2 to 1 and 6 the edges. So it is this one. Okay, and the next is the adjacency list for 3. Okay, and 4. Okay, so totally there are 5 vertices. Okay. And we can calculate the number of edges using this formula, size of edges divided by size of, say, one edge. So that will give us the total number of edges. And then we construct the graph using its constructor. We provide edges, okay, the number of edges, the number of vertices. Okay. So this constructor. Okay. And then we display it. Okay. We print it out. Okay. And now let's compile and run this program. Then you can see how it works. So let's copy this. Okay. So copy. Okay. And then now let's try to compile it. Yeah, so we call this maybe graph adj.cpp. And then we paste it. Okay, so this is the program we just copied. Okay, let's save it. Okay. So you can see that this is what we just discussed. Okay. And now we can compile this. G++, so give it a name. Graph 8. So no error. So we generate the executable and we can execute. So as expected, it displays the adjacency list. Okay, so the CO1, 50, okay, and then CO2, 30, CO3, 100, CO4, 10. So this is the adjacent list for vertex 0. Yeah, you can, if you want, you can put an arrow between these two nodes. Okay. So this is the adjacency list for 2, okay, for vertex 3, okay, for vertex 4. Okay. So this is the implementation of adjacency list in C++. Okay. So you can try that with different graphs. All you need is to provide the edges. Okay, you can construct. Then you can construct a graph. Okay. Well, yeah. Thank you for watching.